The field of pharmacogenomics can be traced back to observations made in the 1950s and 1960s. Researchers noticed individual differences in drug response and adverse reactions, which raised questions about the role of genetics in drug metabolism and efficacy. One of the earliest examples of pharmacogenomics is the discovery of the association between glucose 6-phosphate dehydrogenase, or G6PD, deficiency and adverse reactions to antimalarial drugs like primaquine. This finding highlighted the role of genetic variations in drug response. In the 1980s, researchers discovered that variations in the TPMT gene influence the metabolism of the anti-cancer drug mercaptopurine. Individuals with low TPMT activity were found to be at increased risk of severe toxicity when treated with standard doses of the drug. The discovery of the CYPUD6 gene's role in metabolizing the antihypertensive drug debrioquine marked a significant milestone in pharmacogenomics. Researchers found that certain individuals had reduced CYP2D6 activity, leading to drug accumulation and increased risk of adverse effects. The completion of the Human Genome Project in 2003 was a landmark achievement that provided a comprehensive map of the human genome. This breakthrough laid the foundation for pharmacogenomics research by identifying genetic variations associated with drug response and metabolism. The discovery of genetic variants in the CYP2C9 and VKORC1 genes linked to warfarin response revolutionized anticoagulant therapy. Understanding an individual's genetic profile for these genes helps predict the optimal dose of warfarin, reducing the risk of bleeding or clotting complications. The U.S. Food and Drug Administration, or FDA, has been actively involved in guiding the integration of pharmacogenomics into drug development and clinical practice. The FDA issued its first guidance on pharmacogenomics in 2005, providing recommendations for incorporating genetic information in drug labels. In recent years, pharmacogenomic testing has become more accessible and widespread. Several healthcare institutions and clinics have integrated pharmacogenomic testing into their clinical workflows, enabling personalized treatment decisions based on individual genetic profiles. These milestones highlight the progression of pharmacogenomics from early observations to the current era of personalized medicine. They demonstrate the growing recognition of genetic variations as key factors influencing drug response and the increasing application of pharmacogenomics in clinical practice. The field continues to advance, with ongoing research and discoveries expanding our understanding of the genetic basis of drug response and shaping the future of precision medicine.